Okay, I've made quite a few changes to the plans, so I need to get you guys caught up. What you're looking at is my test shredder assembly. This is not necessarily representative of what we're going to end up with, but this is designed to allow me to prototype a lot of different things in this one box. These shear plates down here are just pieces of flat bar like this, but this is not what it's going to look like when it's done. And as you can see, I've got wooden spacers in there, which are also just temporary. In fact, I've tried a lot of different sizes and thicknesses in order to get these details worked out. And these are all experiments to try to perfect what I can make here. What I was trying to figure out with these various spacers is what kind of tolerance do you need for the spacing in between. And you just saw the answer when that peat bottle got drawn into the shredder, and instead of being ripped apart, it just got wrapped around the blades. That's because there's too much space in between these spacers here, the shear plates, and the knives, so there's nothing to shear it off. It basically can fall into the gap, and then it gets wrapped around your shredder assembly. And of course, that's not what we want. Now, in Dave's plans, what he calls for is about a 3/16 plate for the knives, and then a 1/4 inch for the spacers. And so if you have it fabricated that way, then you're looking at only about a millimeter gap in between all of the knives. And that was the gold standard that I was trying to achieve, and I found that the smaller spacers worked much better. This just happened to be the last setup that I tried, and so this is when I decided to turn the camera on. But the really small ones work the best. That would be this one. Now that we've got that worked out, I was ready to cut steel. Initially, I'd never planned to use wooden washers, although I had those in my test assembly in the first video. I didn't really explain why they were there, and it's just because wood's easy for me to cut. That's what matches my tools. Now, my plan was actually to use rubber spacers. I have this industrial grade rubber. It's embedded with this fabric. It's really tough, and it doesn't bend like you would expect rubber to. This is the rubber that they put on the wall to protect the wall in blast booths when they're blasting the paint off of steel structures. They want to protect the walls, and they use this rubber. I thought this was going to be great, but once I measured it, it wasn't quite thick enough. Remember, your spacer needs to be just barely thicker than your blades, and this is actually just a bit thinner. So I tried to compensate for that by gluing on some smaller pieces of rubber, which is not the industrial grade rubber. But once I put it all in the assembly, this extra layer of rubber fully compressed, and then I was right back to having a spacer that was too small. So even though this would have been neat, it would have given me a lot of frictional force, it just turned out to be the wrong size. You can't just go to the hardware store and buy this stuff, so that was another reason for me to bail on the rubber. What I'm actually going to use is just steel spacers. I've got a 1/4 inch flat bar. Well, I need it to be just a bit thicker, so I made these little shims. This is the wall of a washing machine. I cut off a piece, I measured it, and it's exactly 1 millimeter thick. So I'm going to use this like a shim for all of my spacers, and now I've got steel spacers, and I know that I've got a good size here. Several of you recommended that I use lock washers in between. I was pretty excited about that idea for about 30 seconds, and then I remembered washers don't come in a consistent thickness. There's no reason for them to have a very tight tolerance, and so the thickness is going to vary for both lock washers and regular washers. And also remember, the washer has to be thicker than my 1/4 inch plate here, so I'd have to buy an oversized washer that also had a really tight tolerance for the thickness, and that would just raise the cost more than I thought was necessary. So another thing that was highly suggested, which I may still do, is to drill a hole through the spacers as well as my knives. and then run a pin through them. So I could take a rod like this and just run it through the whole assembly. This rod would then be in double shear, and that would make you'd have a heck of a time breaking this rod in that position. And so that's a really good idea. I like that one. Thank you for those who recommended it. And I may end up doing that if it turns out that the friction from the clamp load is not enough. What we ended up with for now is I have a lock washer here. I've got the one nut on this side and one nut on this side. And so far in my testing, that has held up really good. Even when things got jammed in there, these did not shift. The motor stopped. I ran out of horsepower before the knives slipped. My wrench has two holes in it that are exactly 10 inches from the center of rotation on the end of my wrench. Well, the way I did this is I had my grip pliers on this side locked and pressed against here. Then I took a fish scale and I pulled on the wrench while the other side was locked. What I found was it took about 40 pounds of pulling force here, 10 inches out, and I'll tell you what the clamping load is. I'll put the clamping load on the bottom of the screen. I can't remember off the top of my head. But with 40 pounds of pulling, that was enough to flatten the lock washer. And then I continued to pull until I got to about 70 pounds of pulling force here, 10 inches away from the center. And that felt like it was tight enough that it would hold it nice and steady, so I didn't try to go any tighter than that. So it may turn out that friction is going to be good. In fact, the coefficient of friction between wood and steel is less than steel on steel. I should have a higher frictional force between these steel washers and the blades. There's one more thing I need to tell you. First, how I made these washers. The tricky part is how do you handle it if the outside is really thin. What I ended up doing was I took a hole saw, a 2-inch hole saw, and I started the cut about 1/3 of the way through on one side. I cut about 1/3 of the way through, I flipped it over, cut about 1/3 of the way too, and that way I've got a line scored all the way around for the 2-inch hole saw. Then I took my 1-inch hole saw, went all the way through so that I have my, my hole in the center. And then I went back to the 2-inch hole saw and finished it. When you do it that way, this will stay laying on the table. You don't have to worry about digging it out of the hole saw, and you don't have to try to figure out a way to hold onto this outside while you're drilling a hole on the inside. There may be some other methods for approaching that. I'd love to hear what you guys come up with, but that seemed to work really well for me, so that's the approach I'm going to recommend for now. Now, of course, if you work with steel, you've got all kinds of other options for tools, so you got to keep in mind we're talking about something a woodworker might have. The one final thing about the shredder assembly is the shear plates down here at the bottom. It turns out that the gap between the spacers and the shear plates is really important. So what I'm going to do is I'm going to try to save these pieces that I've already made, and I'm going to go back and cut out a notch right here with the hole saw. And so if I use a 2-inch hole saw, I should end up with the thickness of the hole saw as my gap going all the way around. Now, of course, I got to be careful about the height and make sure I've got the height right, but I can shim that up under the bottom and get the space in between these two exactly where I want it. And that should minimize the gap between my spacers and what I'm just calling my shear plate here. The shredder assembly itself, I think I am going to go ahead and make it out of wood. I haven't thought of a reason why it needs to be made out of steel. The components that are actually shearing off the plastic, I want those to be made out of steel. Those surfaces need to be wear resistant. And I may even go so far as to cut up some more of that washing machine and line the inside of my wooden container with sheet metal. And that'll just be 1 millimeter thick. Now, some of you were concerned that the forces might be too much for wood. There are two factors that go into the strength of your structure. One is the strength of the material itself, which there's no question steel is significantly stronger than wood. Nobody's saying that, okay? Steel is the ultimate readily available resource. But wood is also very strong. In fact, the house that you're in right now is mostly made out of wood. There's the strength of the material, but there's also the geometry of the material. Let me show you an example. Okay, we've got our structure here that needs to support a load. We apply the load, and we see we've got this massive deflection here, okay? Kind of like a diving board. We don't want that, so a common mistake that people make, both woodworkers and even professionals, is we think, one, well man, I need a stronger material, or two, maybe I need more material, let me just make it fatter. So let's try that. Okay, so we have literally doubled the thickness of the material now. Let me find the end of the shorter ruler because that's where we put the load. So I've doubled the thickness, I've got a strong material. Maybe we need to look at another variable. And that other variable is geometry. If you take it and you stand it up like this, not a bit of deflection. The same material. In fact, it's less material now. And it could hold many times more load without any deflection at all. So the same principle applies to wood. If you're smart about your design and you put support in the right areas, in particular, you've got the right amount of depth in the direction of your load, that's going to give you sufficient stiffness. Usually strength and stiffness come together, not always, but that's going to give me a structure that can withstand the loads that we have here. Am I saying that this can definitely be made out of wood? I don't know for sure yet. What I'm going to do, I'm going to be smart about this. I'm going to design my shredder box first. This is what's going to determine what kind of loads I really have, and then I'll work my way out and use that to decide where I need to have my supports and how strong the structure needs to be. In the end, we may determine that, you know what, in order to be sure that it's going to be durable and strong, it needs to be made out of steel. But I haven't made that determination yet, and so far it's looking like wood is going to hold up just fine. That is for the outer casing. But I do want to be sure that my inner lining is going to be wear resistant because it's going to be abraded by plastic, hopefully for years and years. With that in mind, even steel tools get dull with time, right, with use. So wood would also abrade and wear off faster than steel. So I am leaning towards putting some kind of sheet metal on the inside, but I haven't committed to doing that yet either. Let's pull away from the shredder box now and let's talk about power, specifically horsepower. Right now you're looking at a 3/4 horsepower single phase induction motor, and over here you've got a 1/2 horsepower induction motor. Now I think the first question that people are probably having right now is, well, how do you sync the two? Aren't they going to run at slightly different speeds, and aren't you concerned about one side driving more than the other? And actually that's the beautiful thing about induction motors, and that's why I'm recommending that you use an induction motor. I'll tell you why I don't like the other ones here shortly. Induction motors are very reliable in running at a consistent speed because the power company puts out a consistent line frequency. So here in the US, it is 60 hertz. This motor is the magnetic field is rotating at 60 hertz. What that means to you is that it's gonna run at a very consistent speed. And even when there's a load applied, because that magnetic field is getting stronger when the shaft slows down, it tries even harder, it draws more current in order to catch back up and run at a consistent speed. So even if one motor is working a little bit harder than the other, which is what I expect when they have different size motors, they're still going to be chasing that line frequency, and they're going to run at the same speed, just like a man and a woman riding a tandem bicycle. One can be pushing harder while they both pedal at the same rate. That's what makes induction motors great for shredders, not only because you can use more than one, but also because even when a load is applied here, the motor is going to work harder in order to keep the same shredder speed going. Now, laying back here in the back, I do have a rather large DC motor, permanent magnet DC motor. On the label it says it's 2 1/4 horsepower. And so you might look at that and think, well man, you know, why don't you just use that one? Why do you have two motors that together don't add up to the horsepower produced by that one? And the reason is the speed. See, speed is a factor in horsepower. That motor has to run at 6,000 RPM to produce 2 1/4 horsepower. These spin at a much lower rate. Right now they're wired to run at 1140 RPM. They both have multiple windings. This one can run at 1700 and 1140 RPM. This one can run at 1750, 1140, and 850. It's got 3 speeds, and thus it's got 3 sets of windings on the inside. So these are much more configurable. I got these two both of these came from washing machines that I picked up on the side of the road. And I already told you about all the benefits of induction. So back to the DC motor, I certainly have the capability to run this guy at lower speeds, but once you lower the speed down to 70 RPMs, the torque that's available from a permanent magnet motor, it'll barely shred paper. So if you try to run it at lower speeds, you're going to end up with not nearly enough power. If you run it at full speed, you definitely don't want these guys spinning at 6,000 RPM. You're going to have to find a way to get a really significant reduction, that is 6,000 RPM down to about 70 or 80. Now, in the first video, I showed you a linear actuator that I was trying to use to get the kind of speed reduction I wanted. Again, that was assuming I was going to use that motor. As I kept working with it though and thinking about it, I needed to add more and more elements in order to stabilize it and make it so that I could transmit the power the way I wanted. But the short version of the story is, the linear actuator I thought was just not practical if I wanted this to be something that a lot of people can do and not just this special contraption that I've worked out myself. Another option I considered was some kind of direct drive where I would use the gearbox from a washing machine. I've taken apart a lot of washing machines and I've never paid attention to this before, but this is pretty neat. So on the inside you can see that there's a gear reduction here, and there's your main shaft. But you got this interesting contraption in there as well. You can see that there are gear teeth here, and then on the other end there are just a couple of gear teeth on this side. So it turns out you don't actually get a gear reduction. Well, you get a gear reduction, but you get an additional motion as well. So if you look very carefully at this shaft, I'm going to spin the end that the motor's attached to. You see that? Now, first, that is genius. I love that design, and it's great for agitating the clothes and washing clothes, but it is horrible for a shredder. I need that gear reduction to come all the way out on the output shaft. So after tinkering with it for a while, I figured out how it works. There's a big spring that's on here, which I can't find it right now, and when the motor is spinning in one direction, you get the agitation motion. You get that agitation with the tub rotating back and forth, oscillating like this. When you reverse the rotation of the motor, that spring actually grips the entire gearbox and spins the entire assembly, which spins the whole tub. So it's really a very cool mechanism. It's sort of bittersweet. I was excited to have a gearbox that might be readily available to DIYers, and then I realized that you can't really use this the way it is. I decided to go back to V-belts because I was hoping to simplify the design even more. But if you're going to use a V-belt, you need to be sure that you have done everything you need to do to prevent slippage. Now, there are a couple of factors that go into a belt slipping. Number one is not having enough tension on the belt. That's the most obvious one, right? And you might be tempted to just push it tighter until your belt is completely taut, but you don't want that. You see how I've got a little bit of flex in the belt? That's actually a good thing because the belt is not perfect. So if the belt is pulled tight like a guitar string, all the imperfections of the belt going around the small pulley is going to cause huge vibrations, and all of that will be transmitted into your system. And you don't want your whole system vibrating because of the belt. If you leave it slack, the belt can flop around and that energy can be wasted flopping the belt around, and it doesn't get driven into your system. So a little bit of slack is good, but you do need to make sure you've got enough tension on the belt. The second thing is you need to make sure your pulleys actually match your belt. Now this is an A style belt and the pulleys are also A. Sometimes they'll say 4L, that's another type of belt. Actually I think 4L and A are equivalent as far as the groove diameter and angle and all of that. I'll have to double check that. But so 4L and A I think are equivalent as far as the shape. But you need to make sure they match, especially if you're using salvaged equipment like I do. The belts are going to vary a lot, so you do just want to check that and make sure that you've got a good fit there. And the last thing is a concept called wrap. And that is about how much engagement your pulley actually has with the V-belt. The more wrap you have around your pulley, the better the grip your pulley is going to have on the belt. So you have to resist that temptation to use a really small pulley like this, which is only 1.5 inches. If I go this small, I've got to push it out and make it tighter, and then I'm only going to have a very small percentage of wrap. To illustrate the difference, I've actually set this up with these pulleys on there, and I'll show you that clip right here. You can see that the speed is slower, but when I put something in there that's a little bit tougher to cut, the belt starts slipping, and that's because you don't have good wrap. So according to my Shigley's engineering book here, Mechanical Engineering Design, it says that the minimum size pulley you should use for a V-belt is about 3 inches. And it also says that the distance, the center distance between your two pulleys should not be more than 3 times the sum of the two diameters. So in this case, it'd be 14 plus 2.5 times 3. That will be the greatest distance. The smallest distance between centers should not be more than the diameter of your large pulley. So in this case, it would be 14 inches. I'm actually sitting right at 15 inches now, so I'm really close to the smallest center to center distance. So by now, I'm sure you're wondering what this guy is all about. That is a 3-phase, 1 horsepower industrial grade motor with one big honking gearbox hanging on the end of it. And this is actually what I intend to build my shredder with. All right, I've got some explaining to do. So all throughout, ever since I started thinking about making a shredder, I have been searching for a gearbox. And I decided I would be really diligent. Every morning and every night, I would check Craigslist and all the local listings. It took about 3.5, 4 weeks, and I finally found one. It was a 2.5 hour drive away, and the guy was selling 6 of these motors, 4 gearboxes, and he wanted $400 for everything. I sent him a message and I said, I just want to confirm, do they work? Do you have 3-phase power so that we can plug them in and check them? And he said no. So I said, well, if I got to take them as is and it's going to take me 2.5 hours to get there, you know, I will offer you $300 without even seeing them, and I'm willing to drive and pick them up, you know, if you'll take that. And he accepted my deal. So for $300, I got 6 of these industrial motors and 4 of these massive gearboxes. So you might be wondering then, if I got this thing, then why in the world am I still bothering with all of this? And that's an excellent question. The answer is really simple. If I wanted to just make a shredder for myself, I would have just had everything made the way Dave designed it, went to my friend's house and welded it up. He has a welder, I have the PPE that I need. I could have got this done last week. But my goals are bigger than that. I want to take Dave's vision, this amazing thing that he's done, and I want to make it accessible to those who don't have metalworking tools, because there are many of us out there. Now, in the future, I plan to get a welder, and I want to get a metalworking lathe, and I've got a lot of plans for working with steel. I don't have any objection to steel working, but there are also many people who would like to make things out of plastic and start working with HDPE. But, you know, they don't have metalworking tools, and that's the barrier that I'm trying to cross with this series of videos. So hopefully that clears things up for you. So here's how you can help. There's a couple ways. One, you can share this video. That will be helpful so that we can get a lot of feedback. Number 2, post your ideas down below. If you see me working on something and you think there's a better way to do it, man, I mean, I'm taking all the hints that I can on this. This has been quite the challenge to try to simplify this. I'm really excited about where this is going. I've got a couple more little things to get worked out. I feel like the structural design for the final overall assembly is the easy part. Once I know what kind of forces I got here, then designing a structure that can support it, I'm not terribly worried about that. But I would love more feedback on the shredder assembly itself, and especially the powertrain. Now that you guys have an idea of kind of what you need, we're definitely looking for some kind of induction motor. We mostly just got to think about how to make a simple transmission of power, either through belts, or if you can find a gearbox, especially if you're diligent and you search online, you may be able to purchase something for a great price. So let me know what you think. And if you guys have other ideas about ways that we can get a gearbox that doesn't oscillate, I would love to hear it. So I'm really excited about where this project is going. Hit the subscribe button if you're not a subscriber so you can get notified when the next video comes out. And I'll see you guys pretty soon. Thanks for watching.